Imagine two of the most powerful objects in the universe, black holes, locked in a cosmic dance, spiraling closer and closer together. What happens when they finally meet? Can two black holes actually merge into one? And if so, what does that mean for the universe, for space and time, and even for us? Today, we're diving into one of the most mind-bending, awe-inspiring mysteries in all of astrophysics. A story that stretches from the tiniest quantum ripples to the grandest scales of the cosmos. If you're fascinated by the universe's biggest questions, make sure to subscribe to this channel and give this video a thumbs up. And one quick question: if you could witness any cosmic event up close, like a black hole merger, a supernova, or the birth of a star, what would you choose? Let me know in the comments down below. I'll pin the most creative answer. Now let's begin. First, let's get clear on what a black hole actually is. A black hole isn't a thing in the usual sense. It's a region of space where gravity is so strong that nothing, not even light, can escape. At the center is the singularity, a point where our current understanding of physics breaks down. Surrounding it is the event horizon, the boundary beyond which nothing returns. Black holes come in different sizes, from stellar mass black holes formed by collapsing stars to supermassive black holes, millions or even billions of times the mass of our Sun, lurking at the centers of galaxies. But can two of these cosmic monsters actually merge? The answer is yes, and we have proof. In fact, the first direct evidence came in September of 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the very first time. These ripples in space-time were created by two black holes, each about 30 times the mass of the Sun, spiraling together and merging into a single, larger black hole. The energy released in that moment was so immense that for a fraction of a second, it outshone all the stars in the observable universe. Yet it was invisible to our eyes, detectable only as a faint tremor in the fabric of space-time itself. So how does this cosmic collision actually happen? It starts with two black holes orbiting each other, usually after the death of two massive stars in a binary system. Over millions or even billions of years, they lose energy by emitting gravitational waves, tiny ripples that carry energy away at the speed of light. As they spiral closer, the waves grow stronger and more frequent, until finally, in the last few seconds, the black holes accelerate to nearly half the speed of light and smash together in a violent merger. But the story doesn't end there. The newly formed black hole is often left spinning, and it can ring like a struck bell, emitting more gravitational waves as it settles down. This final ringdown phase is a key signature that scientists look for when analyzing gravitational wave data. It's like hearing the echo of a cosmic bell that was struck billions of years ago in a galaxy far, far away. What's truly astonishing is that these mergers are not rare. Since that first detection in 2015, LIGO and its European partner, Virgo, have observed dozens of black hole mergers, each one telling a different story about the lives and deaths of stars, the growth of galaxies, and the evolution of the universe itself. Some of these black holes are much bigger than we expected, challenging our theories of how stars live and die. Others are spinning at incredible rates or merging in ways that suggest they formed in dense star clusters or even in the chaotic centers of galaxies. But why do black holes merge at all? The answer lies in gravity's relentless pull. When two black holes are close enough, their mutual gravity locks them into a binary system. Over time, they lose energy through gravitational radiation, drawing them ever closer. This process is incredibly slow at first, but as the black holes approach, the energy loss accelerates dramatically. In the final moments, the two event horizons touch and merge, creating a single, larger event horizon that quickly settles into a new, stable black hole. The idea of two black holes merging isn't just a wild theory, it's a phenomenon that's now at the heart of modern astrophysics. But to truly appreciate how extraordinary these events are, let's step back and look at the cosmic context. Black holes are not just isolated monsters lurking in the darkness. They are woven into the very fabric of the universe's story, from the first stars to the largest galaxies. Let's start with how black holes come to exist in pairs in the first place. Most stars are born in clusters, and many are part of binary or even multiple star systems. When two massive stars orbit each other, they live fast and die young, burning through their fuel in just a few million years. When each star reaches the end of its life, it can explode as a supernova, leaving behind a neutron star, or, if it's massive enough, a black hole. If both stars in the binary are massive enough, you end up with two black holes orbiting each other, a binary black hole system. But the universe is a chaotic place. Sometimes black holes can also pair up in dense environments like globular clusters or the crowded centers of galaxies. In these places, stars and black holes are packed so tightly that gravitational interactions can fling objects around like cosmic billiard balls. Two black holes might find themselves close enough to become gravitationally bound, starting their slow spiral toward each other. Now here's where things get really interesting. As these black holes orbit, they emit gravitational waves, tiny ripples in space-time predicted by Einstein's general theory of relativity in 1915. For a century, these waves were purely theoretical, but in 2015, LIGO changed everything. The observatory's twin detectors in Louisiana and Washington are so sensitive they can detect distortions in space-time smaller than a proton's width. When a gravitational wave passes through Earth, it stretches and squeezes space itself ever so slightly, and LIGO's lasers pick up this minuscule change. The first detection, known as GW150914, was a cosmic milestone. Two black holes, one about 36 times the mass of the Sun and the other about 29 times the Sun's mass, merged to form a single black hole of about 62 solar masses. The missing mass, about 3 suns worth, was converted directly into gravitational wave energy. For a brief moment, the power output was 50 times greater than all the stars in the observable universe combined. Since then, LIGO and Virgo have detected dozens of black hole mergers, each with its own unique story. Some involve black holes of similar mass, while others are wildly mismatched. Some mergers happen in the quiet outskirts of galaxies, while others occur in the bustling centers where stars and black holes are constantly interacting. Each detection is like a postcard from a different corner of the universe, sent across billions of years. But what actually happens during a black hole merger? The two black holes orbit each other, gradually losing energy to gravitational waves. This phase can last millions or even billions of years, depending on how close the black holes are and how much mass they have. The orbits slowly shrink and the black holes spiral closer together. As the black holes get closer, the gravitational waves they emit become stronger and more frequent. In the final seconds, the black holes are moving at a significant fraction of the speed of light. Their event horizons touch and merge, forming a single, larger event horizon. This is the moment of maximum gravitational wave emission, the chirp, that LIGO and Virgo detect. The newly formed black hole is not perfectly smooth at first. It rings like a struck bell, emitting gravitational waves as it settles into a stable, spinning shape. This phase is short, lasting just milliseconds, but it carries crucial information about the final black hole's mass and spin. The entire process is over in less than a second, but the story it tells is written across billions of years and trillions of kilometers. Now you might be wondering, what does a black hole merger look like? The answer is both simple and profound. It doesn't look like anything in the traditional sense, because no light escapes from inside the event horizons. But the merger can have dramatic effects on the surrounding environment. If there's gas or dust nearby, the violent shaking of space-time can heat it up, causing it to glow in X-rays or even visible light. In rare cases, astronomers have observed flashes of light coinciding with gravitational wave detections, suggesting that some mergers happen in gas-rich regions. But the real fireworks are in the gravitational waves themselves. These ripples travel across the universe at the speed of light, carrying information about the masses, spins, and even the orientation of the merging black holes. By analyzing the shape and frequency of the waves, scientists can reconstruct the entire event, like listening to a symphony and identifying each instrument by ear. The implications of black hole mergers go far beyond astrophysics. They are testing grounds for Einstein's theory of general relativity in the most extreme conditions imaginable. So far, every observation matches Einstein's predictions perfectly, but scientists are always on the lookout for deviations that could hint at new physics, perhaps clues to quantum gravity or the true nature of space-time. Black hole mergers also play a crucial role in the evolution of galaxies. When two galaxies collide, their central supermassive black holes can eventually find each other and merge. This process releases enormous amounts of energy, shaping the structure of the resulting galaxy and possibly triggering bursts of star formation. The gravitational waves from these supermassive mergers are too low in frequency for LIGO to detect, but future observatories like the space-based LISA mission will be able to hear them. Let's zoom out even further. Black hole mergers are not just isolated events, they are part of the universe's grand recycling program. When two black holes merge, the resulting black hole can go on to merge again, building up ever larger black holes over cosmic time. This hierarchical growth may explain how supermassive black holes, with masses of millions or billions of suns, formed so quickly in the early universe. But there are still mysteries. For example, some black holes detected by LIGO and Virgo are heavier than we thought possible from normal stellar evolution. These mass gap black holes might be the result of previous mergers, or they could hint at new physics like the collapse of exotic stars or even primordial black holes formed in the early universe. The story of black hole mergers is also a story of human ingenuity. The technology required to detect gravitational waves is among the most precise ever built. LIGO's mirrors are polished to atomic smoothness, and its vacuum tubes are the longest in the world. The data analysis requires supercomputers and sophisticated algorithms to sift through the noise and find the faint signals from distant mergers. And the discoveries keep coming. In 2019, LIGO and Virgo detected a merger between a black hole and a neutron star, the first ever observed. This event, known as GW190425, opened a new chapter in multimessenger astronomy, where gravitational waves and electromagnetic signals are combined to give a fuller picture of cosmic events. The future is even more exciting. The next generation of gravitational wave detectors, like the Einstein telescope in Europe and the Cosmic Explorer in the United States, will be even more sensitive, able to detect mergers from the earliest epochs of the universe. Space-based observatories like LISA will open up the low-frequency universe, revealing mergers of supermassive black holes and possibly even exotic objects like cosmic strings. But perhaps the most profound aspect of black hole mergers is what they tell us about our place in the universe. Every time we detect a gravitational wave, we are listening to the echoes of a cosmic event that happened billions of years ago in a galaxy we may never see. The atoms in your body were forged in stars that lived and died long before our sun was born. The gravitational waves passing through you right now are reminders that we are connected to the universe in ways we are only beginning to understand. The more we learn about black hole mergers, the more they challenge our imagination and expand our sense of what's possible in the universe. These events are not just rare cosmic accidents, they are a fundamental part of how the universe evolves, recycles, and grows. Every black hole merger is a chapter in the story of cosmic structure, galaxy formation, and even the ultimate fate of matter and energy. Let's take a closer look at what happens right before, during, and after two black holes merge. As the black holes spiral closer, they emit gravitational waves that grow stronger and more rapid. In the final seconds, the frequency of these waves increases dramatically, creating what scientists call a chirp. This chirp is the signature LIGO and Virgo look for, a rising tone that ends abruptly as the two event horizons merge into one. The energy released in this instant is so immense that for a brief moment, the merging black holes outshine the entire visible universe in gravitational wave energy. But what happens to the new black hole after the merger? The answer is just as fascinating. The newly formed black hole is often spinning rapidly, and it can be kicked at high speeds, sometimes thousands of kilometers per second, by the asymmetric emission of gravitational waves. In some cases, this kick is strong enough to eject the black hole from its host galaxy entirely, sending it drifting through intergalactic space. Imagine a black hole, heavier than dozens of suns, wandering alone between galaxies, carrying the memory of its violent birth. The aftermath of a black hole merger can also have dramatic effects on the surrounding environment. If the merger happens in a region rich with gas and dust, the violent shaking of space-time can trigger shock waves, heating up the material and causing it to glow in X-rays or even visible light. In rare cases, astronomers have observed flashes of light coinciding with gravitational wave detections, suggesting that some black hole mergers are not entirely dark after all. But perhaps the most mind-bending aspect of black hole mergers is what they reveal about the nature of space and time. When two black holes merge, they create a region of space-time so warped that our current theories struggle to describe it. The event horizon grows, the singularity deepens, and the very fabric of reality is stretched to its limits. This is where general relativity meets quantum mechanics, and where new physics may be waiting to be discovered. If you find this idea fascinating, you'll love my video, What If Our Universe is Inside a Black Hole? In that episode, we explore the wild possibility that our entire cosmos could be the interior of a black hole in a higher dimensional universe. The connections between black holes, space-time, and the origins of everything are deeper and stranger than anyone imagined. The link is in the description and on the card above. Back to black hole mergers. One of the most exciting frontiers is the study of supermassive black holes at the centers of galaxies. When galaxies collide, their central black holes can eventually find each other and begin a slow, spiraling dance that can last hundreds of millions of years. As they get closer, they stir up the gas and stars around them, creating tidal waves of energy that can trigger bursts of star formation or even shut down starbirth by heating and expelling gas. Eventually, the two supermassive black holes get close enough that gravitational wave emission takes over, and the final merger happens in a spectacular burst of energy. These events are so powerful that they can reshape entire galaxies, sending out jets of material at nearly the speed of light and creating ripples in space-time that travel across the universe. The upcoming LIGO mission, a space-based gravitational wave observatory, will be able to detect these low-frequency waves, opening a new window on the most massive mergers in the cosmos. But even smaller black hole mergers have profound consequences. When two stellar mass black holes merge, the resulting black hole can go on to merge again, building up a hierarchy of ever larger black holes. This process, known as hierarchical merging, may explain how some black holes detected by LIGO and Virgo are much heavier than any single star could produce. It's a cosmic assembly line, building bigger and bigger black holes over billions of years. The study of black hole mergers is also revealing new clues about the environments where they form. Some mergers happen in isolated binary systems, where two massive stars are born together and evolve side by side. Others occur in dense star clusters where gravitational interactions can bring black holes together in chaotic three-body encounters. Still others may happen in the accretion disks of supermassive black holes where gas and stars are packed so tightly that collisions are inevitable. Each of these environments leaves its own fingerprint on the gravitational waves we detect. By analyzing the properties of the merging black holes, their masses, spins, and even the angles at which they collide, scientists can reconstruct the story of how and where the merger happened. It's like being able to read the biography of a black hole from the ripples it sends across the universe. But there are still many mysteries. For example, some black hole mergers detected by LIGO and Virgo involve objects in the so-called mass gap, a range of masses where we didn't expect to find black holes at all. These discoveries are forcing scientists to rethink their models of stellar evolution, supernova explosions, and the formation of compact objects. Are these black holes the result of previous mergers, or do they hint at new physics like the collapse of exotic stars or even primordial black holes from the early universe? The detection of gravitational waves from black hole mergers has also opened up a new era of multi-messenger astronomy. In some cases, astronomers have been able to observe both gravitational waves and electromagnetic signals like gamma-ray bursts or flashes of light from the same event. This combination of messengers gives us a much richer picture of what's happening, allowing us to test theories of gravity, matter, and energy in the most extreme environments known. The future of black hole merger research is incredibly bright. As gravitational wave detectors become more sensitive, we'll be able to detect mergers from farther away, including those that happened in the early universe. Space-based observatories like LISA will allow us to hear the mergers of supermassive black holes, while ground-based detectors will continue to catch the stellar mass mergers happening all around us. But perhaps the most profound lesson of all is what these events tell us about our own place in the universe. Every black hole merger is a reminder that we are part of a cosmos that is dynamic, interconnected, and constantly evolving. The atoms in your body were forged in stars that lived and died billions of years ago. The gravitational waves passing through you right now are echoes of events that happened before Earth even existed. We are stardust, yes, but we are also the children of black holes, shaped by the most powerful forces in the universe. The implications of black hole mergers extend far beyond the events themselves. These cosmic collisions are reshaping our understanding of fundamental physics, challenging our theories, and opening new windows into the nature of reality. Let's explore some of the deeper questions that arise from these extraordinary phenomena. One of the most profound mysteries is what happens to information when black holes merge. According to quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or transformed, but never truly lost. Yet when matter falls into a black hole, it seems to disappear forever behind the event horizon. This is the famous information paradox. And black hole mergers make it even more puzzling. When two black holes merge, what happens to the information that was trapped inside each one? Does it combine in some way, or is it lost forever? Stephen Hawking spent decades wrestling with this paradox, eventually proposing that black holes slowly evaporate through a process now known as Hawking radiation. But even this doesn't fully resolve the issue. Black hole mergers happen so quickly and violently that there's no time for Hawking radiation to carry away the information. Some physicists believe the answer lies in the holographic principle, the idea that all the information inside a black hole is actually encoded on its two-dimensional surface, like a hologram. If this is true, then when two black holes merge, their surfaces combine in a way that preserves all the information, even if we can't access it from the outside. The study of black hole mergers is also revealing new insights into the nature of gravity itself. Einstein's general relativity has passed every test we've thrown at it, but physicists know it can't be the final word. At the smallest scales where quantum effects become important, general relativity breaks down. Black hole mergers probe the regime where gravity is strongest, potentially offering clues to a quantum theory of gravity. Some theories predict tiny deviations from Einstein's predictions. Perhaps gravitational waves travel slightly slower than light, or maybe the merger creates exotic particles we've never seen before. So far, no such deviations have been detected, but the search continues. Another fascinating aspect is the role of spin in black hole mergers. Black holes can rotate at incredible speeds, with their event horizons spinning at a significant fraction of the speed of light. When two spinning black holes merge, their spins combine in complex ways, depending on their orientations. If the spins are aligned with the orbit, the final black hole can end up spinning even faster. But if they're misaligned, the merger can produce a powerful kick that sends the new black hole flying through space at thousands of kilometers per second. These kicks have profound consequences for galaxy evolution. A supermassive black hole ejected from the center of a galaxy takes with it any stars that were orbiting nearby, creating a hyper-compact stellar system, essentially a mini-galaxy centered on a black hole, drifting through intergalactic space. Meanwhile, the galaxy left behind must readjust to the loss of its central black hole, potentially triggering new bursts of star formation or altering the orbits of stars throughout the galaxy. The distribution of black hole masses revealed by gravitational wave detections is also telling us new things about stellar evolution. Before LIGO, most astronomers expected stellar mass black holes to have masses between about 5 and 20 times that of the Sun, based on our understanding of how massive stars evolve and explode. But many of the black holes detected by LIGO and Virgo are much heavier, 30, 40, even 50 times the mass of the Sun. Where do these heavy black holes come from? One possibility is that they formed from the very first generation of stars in the universe, which were made of pure hydrogen and helium with no heavier elements. These population 3 stars could have been much more massive than any star today, potentially leaving behind correspondingly massive black holes. Another possibility is that these heavy black holes are themselves the products of previous mergers, second or even third generation black holes that have grown through successive collisions. The environments where black hole mergers occur are just as important as the mergers themselves. In dense star clusters where thousands or millions of stars are packed into a small volume, gravitational interactions can bring black holes together in ways that would be impossible in the wider galaxy. These dynamical encounters can create black hole binaries with properties very different from those formed through stellar evolution. For example, with spins that are randomly oriented rather than aligned with the orbit. Recent simulations suggest that some star clusters might be veritable black hole factories, producing merger after merger as black holes sink to the center through a process called dynamical friction. The heaviest black holes tend to congregate in the core, where they can form binaries and merge repeatedly. This hierarchical assembly could explain some of the surprisingly massive black holes detected by LIGO and Virgo, but perhaps the most exotic environment for black hole mergers is in the accretion disks around supermassive black holes. In these disks, gas and stars spiral inward, creating a dense, chaotic environment where collisions are common. Black holes embedded in these disks can grow rapidly by accreting gas, and they can also find partners and merge. The gravitational waves from these mergers would carry the imprint of their unusual birthplace, potentially allowing astronomers to identify them among the growing catalogue of detections. The connection between black hole mergers and the early universe is another frontier of research. In the first fraction of a second after the Big Bang, the universe was so hot and dense that black holes could have formed directly from the collapse of dense regions, no stars required. These primordial black holes, if they exist, could range from microscopic to massive, and they might make up some or all of the mysterious dark matter that dominates the universe's mass. If primordial black holes exist, they would occasionally merge, producing gravitational waves with distinctive properties. Some scientists have suggested that a few of the black hole mergers detected by LIGO and Virgo might actually involve primordial black holes, though this remains controversial. Future detectors with greater sensitivity might be able to settle the question by detecting mergers from the very early universe, when only primordial black holes could have existed. The study of black hole mergers is also revealing the complex interplay between different cosmic phenomena. For example, when a black hole merger happens in a gas-rich environment, the gravitational waves can interact with the surrounding material, potentially triggering electromagnetic emissions. In 2019, astronomers reported a possible optical counterpart to a black hole merger detected by LIGO and Virgo, a flash of light from a distant galaxy that coincided with the gravitational wave event. If confirmed, this would open up a new era of multi-messenger astronomy for black hole mergers, similar to what has already been achieved for neutron-star collisions. The future of black hole merger science is incredibly bright. The next generation of ground-based detectors, such as the Einstein telescope in Europe and Cosmic Explorer in the United States, will be 10 times more sensitive than current instruments. They'll be able to detect mergers from the edge of the observable universe, including those that happened when the universe was just a few 100 million years old. This will allow us to trace the growth of black holes across cosmic time and understand how they evolved alongside galaxies and stars. Space-based detectors like LISA will open up an entirely new frequency range, allowing us to detect the mergers of supermassive black holes for the first time. These events are so powerful that they can be detected from billions of light-years away, providing a new probe of the universe's largest structures. LISA will also be sensitive to the gravitational waves from smaller black holes spiraling into supermassive ones, events that could reveal the population of intermediate mass black holes that are thought to bridge the gap between stellar and supermassive scales. But perhaps the most exciting prospect is the unexpected discoveries that await us. Every time we've opened a new window on the universe, from radio waves to gamma rays to gravitational waves, we've found things we never anticipated. Black hole mergers have already surprised us with their frequency, their masses, and their environments. What other secrets are hiding in the gravitational wave sky? As we continue to detect and study these cosmic collisions, we're not just learning about black holes, we're learning about the universe itself. Every merger is a natural experiment in extreme physics, testing our theories in ways no laboratory ever could. Every detection is a fossil from the past, carrying information about the stars, galaxies, and environments that created it. And every gravitational wave that passes through Earth is a reminder that we are part of a dynamic, evolving cosmos where even the most massive objects dance, collide, and merge in an endless cosmic ballet. The technological revolution that made gravitational wave detection possible is a story of human ingenuity pushed to its absolute limits. To understand just how remarkable these detections are, consider this. A typical gravitational wave passing through Earth stretches and squeezes space by about 1 part in 10 to the 21st power. That's like measuring the distance to the nearest star, over 4 light-years away, with a precision better than the width of a human hair. The fact that we can do this at all is nothing short of miraculous. The journey to detect gravitational waves began decades before the first detection. In the 1960s and 70s, Joseph Weber at the University of Maryland built the first gravitational wave detectors, massive aluminum cylinders that he hoped would ring like bells when a gravitational wave passed through. Though Weber claimed several detections, other scientists couldn't reproduce his results, and it became clear that gravitational waves were far weaker than anyone had imagined. The breakthrough came with the idea of using laser interferometry. By splitting a laser beam and sending it down two perpendicular arms, scientists could measure tiny changes in the relative lengths of the arms as gravitational waves passed through. But turning this idea into reality required overcoming countless technical challenges. The mirrors had to be polished to near-atomic smoothness. The laser had to be incredibly stable. The entire apparatus had to be isolated from vibrations, not just earthquakes and passing trucks, but even the motion of atoms in the mirrors themselves. The LIGO project, begun in the 1980s, took decades and hundreds of millions of dollars to reach the sensitivity needed to detect gravitational waves. The original LIGO operated from 2002 to 2010 without a single detection, but it proved the technology could work. Then came advanced LIGO, with improved lasers, better mirrors, and more sophisticated vibration isolation. Within days of turning on in September 2015, it detected its first black hole merger. The success of LIGO has inspired a global network of gravitational wave observatories. Virgo in Italy joined the hunt in 2017, allowing for better localization of gravitational wave sources. Kagra in Japan, built underground to reduce noise, began observations in 2020. Plans are underway for LIGO India, which will further improve our ability to pinpoint where gravitational waves come from. And in the future, space-based detectors like LISA will open up entirely new frequency ranges, allowing us to hear the gravitational wave universe in full stereo. But detection is only the beginning. The real challenge is understanding what the gravitational waves are telling us. When LIGO or Virgo detects a signal, it's not immediately obvious that it's from a black hole merger. The raw data is buried in noise, and sophisticated algorithms must sift through it to find the telltale chirp. Then comes the painstaking process of comparing the signal to theoretical templates, computer simulations of what gravitational waves from different types of sources should look like. These simulations are marvels of computational physics. Solving Einstein's equations for two merging black holes requires supercomputers running for weeks or months. The equations are so complex that they can only be solved numerically, and tiny errors can grow exponentially, ruining the calculation. It took decades of work by teams of physicists and computer scientists to develop codes that could reliably simulate black hole mergers. Now, these simulations are so accurate that they can predict the gravitational waveform to better than 1% precision. The match between observations and theory has been remarkable. Every black hole merger detected so far has matched the predictions of general relativity perfectly within the measurement uncertainties. This is a triumph for Einstein's century-old theory, but it's also a challenge for physicists hoping to find new physics. Many theories beyond general relativity predict small deviations in the gravitational waves from black hole mergers, but so far, no such deviations have been seen. One of the most exciting frontiers is the search for exotic, compact objects that might masquerade as black holes. Some theories predict the existence of boson stars, clumps of exotic particles held together by gravity. Others suggest gravastars, objects with a de Sitter space interior surrounded by a thin shell of matter. Still others propose fuzzballs, string theory's answer to black holes, with no event horizon or singularity. If any of these objects exist, they might merge and produce gravitational waves almost identical to those from black hole mergers, but with subtle differences that could reveal their true nature. The study of black hole mergers is also pushing the boundaries of data analysis and machine learning. With dozens of detections and more coming all the time, astronomers need automated ways to classify events, estimate parameters, and search for patterns. Machine learning algorithms trained on simulated gravitational waves can now identify potential signals in real time, alerting astronomers within seconds of a detection. This rapid response is crucial for catching any electromagnetic counterparts, flashes of light that might accompany some mergers. The astrophysical implications of black hole mergers continue to unfold. By studying the distribution of black hole masses, spins, and merger rates, astronomers are piecing together the life cycles of massive stars and the environments where black holes form. For example, the detection of black holes with masses in the so-called pair instability gap between about 50 and 120 solar masses suggests that our understanding of stellar evolution needs revision. Stars massive enough to produce such heavy black holes were thought to be completely destroyed in pair instability supernovae, leaving no remnant behind. One possible explanation is that these heavy black holes formed in low metallicity environments where stars can grow larger before becoming unstable. This would mean that many of the black hole mergers we're detecting happened long ago, when the universe had fewer heavy elements. The light travel time means we're seeing these mergers as they were billions of years ago, offering a window into the conditions of the early universe. Another puzzle is the origin of black hole spins. If black holes form from the collapse of rotating stars, we might expect their spins to be aligned with their orbital motion in a binary system. But many of the black holes detected by LIGO and Virgo have spins that are misaligned or even anti-aligned with the orbit. This suggests that some binaries form through dynamical encounters in dense environments, where the black hole's spins retain no memory of their original orientation. The connection between black hole mergers and galaxy formation is becoming clearer with each new discovery. Supermassive black holes at the centers of galaxies are thought to grow through a combination of gas accretion and mergers with other black holes. By understanding how stellar mass black holes merge, we can better model the growth of their supermassive cousins. This is crucial for understanding galaxy evolution, since supermassive black holes seem to regulate star formation in their host galaxies through powerful jets and winds. The role of black hole mergers in creating heavy elements is another active area of research. While most heavy elements are forged in supernovae and neutron star collisions, some theories suggest that the accretion disks around merging black holes could also be element factories. If a black hole merger happens in a gas-rich environment, the extreme temperatures and densities could trigger nuclear reactions, creating elements that are then ejected into space. This process might contribute to the chemical enrichment of galaxies, adding another pathway for the creation of the elements that make up planets and life. Looking ahead, the future of black hole merger science is filled with possibilities. As detectors become more sensitive, we'll be able to study the properties of merging black holes in ever greater detail. We might detect the subtle effects of black hole hair, deviations from the perfect smoothness predicted by general relativity. We might catch the gravitational waves from black holes merging with other exotic objects, like neutron stars or white dwarfs. We might even detect the stochastic background, the combined hum of all the black hole mergers happening throughout the universe, too faint to detect individually, but adding up to a cosmic symphony. The philosophical implications of black hole mergers are just as profound as the scientific ones. These events remind us that the universe is not static or eternal, but dynamic and evolving. Even black holes, the ultimate endpoints of stellar evolution, are not permanent. They can merge, grow, and change, participating in the cosmic dance of creation and destruction. In a sense, black hole mergers are the universe's way of recycling its most extreme objects, combining them into ever larger repositories of mass and energy. As we delve deeper into the phenomenon of black hole mergers, we encounter questions that push the very boundaries of human knowledge and imagination. These cosmic events are not just spectacular displays of nature's power, they are laboratories for testing our most fundamental theories about reality, windows into the extreme physics that governs the universe, and perhaps even clues to the ultimate fate of everything that exists. One of the most fascinating aspects of black hole mergers is their role in the cosmic web of cause and effect. Every merger sends ripples through space-time that travel for billions of years, eventually washing over distant galaxies and planets. Right now, as you read these words, gravitational waves from countless ancient mergers are passing through your body. You can't feel them, they're far too weak, but they're there, carrying information about events that happened when the universe was young. In a very real sense, we are constantly bathed in the echoes of cosmic catastrophes. This raises profound questions about the nature of space-time itself. Einstein showed us that space and time are not fixed stages on which events play out, but dynamic entities that can bend, stretch, and ripple. Black hole mergers take this to the extreme, creating distortions so severe that our usual concepts of space and time break down. Near the merging event horizons, time can slow to a crawl, space can twist into pretzel-like configurations, and the very notion of before and after becomes ambiguous. Some physicists have suggested that black hole mergers might even create closed, time-like curves, paths through space-time that loop back on themselves, potentially allowing for time travel. While this remains highly speculative, the mathematics of general relativity doesn't rule it out. The violent distortions of space-time during a merger could, in principle, create configurations that would allow information or even matter to travel backward in time. Of course, nature seems to have safeguards against such paradoxes. The event horizons of the merging black holes would likely hide any such exotic phenomena from outside observers. The quantum aspects of black hole mergers open up even stranger possibilities. According to quantum mechanics, the vacuum of space is not empty but seething with virtual particles that pop in and out of existence. Near the event horizons of merging black holes, these quantum fluctuations can become real particles, a process similar to Hawking radiation but potentially much more intense. Some theories suggest that the violent dynamics of a merger could create a burst of exotic particles, perhaps even particles we've never seen before, remnants of the high-energy physics that dominated the early universe. This connection to the early universe is more than just an analogy. The conditions during a black hole merger, extreme gravity, intense energy density, violent dynamics, are the closest we can come to recreating the environment of the Big Bang. By studying these mergers, we're essentially looking at fossil remnants of the universe's birth preserved in the form of gravitational waves. Every detection is a message from the deep past, encoded in the language of curved space-time. The role of black hole mergers in the universe's future is equally profound. As the universe expands and cools, stars will eventually stop forming, galaxies will fade, and the cosmos will enter what physicists call the degenerate era, a time when only black holes, neutron stars, and white dwarfs remain. In this far future, black hole mergers will be among the few energetic events still occurring, brief flashes of activity in an otherwise dark and quiet universe. But even black holes are not eternal. Through Hawking radiation, they slowly evaporate, with smaller black holes evaporating faster than larger ones. The black holes created by mergers, being more massive, will last longer, potentially surviving for 10 to the 67 years or more. They will be among the last objects in the universe, the final repositories of the mass and energy that once shone as stars and galaxies. This raises a startling possibility. Could black hole mergers be a mechanism for the universe to preserve information about its past? If the holographic principle is correct, and all the information that falls into a black hole is encoded on its event horizon, then mergers might combine this information in complex ways. The final black holes in the universe might be vast libraries containing the encoded history of everything that ever fell into them: stars, planets, perhaps even civilizations. The search for electromagnetic counterparts to black hole mergers has revealed another layer of complexity. While black holes themselves emit no light, the environments around them can be rich with matter, gas, dust, even stars. When black holes merge in such environments, the gravitational disruption can trigger a variety of electromagnetic phenomena. Gas can be shocked and heated, producing X-rays. Magnetic fields can be twisted and reconnected, generating powerful jets. Stars can be disrupted or ejected, creating optical flashes. In 2019, the Zwicky Transient Facility detected what might be the first optical counterpart to a black hole merger, a flare from a distant galaxy that coincided with a gravitational wave event. If confirmed, this would mean that some black hole mergers are not dark after all, but can shine across the electromagnetic spectrum. This opens up the exciting possibility of studying the same event with both gravitational waves and traditional telescopes, giving us a much richer picture of what's happening. The environments where black hole mergers occur are turning out to be far more diverse than anyone expected. While many mergers probably happen in relative isolation, others occur in the hearts of galaxies, in dense star clusters, or even in the accretion disks of supermassive black holes. Each environment leaves its mark on the gravitational waves, encoding information about the conditions where the merger took place. For example, if a merger happens in a dense stellar environment, the gravitational influence of nearby stars can affect the orbit of the binary, causing it to precess or change its eccentricity. These effects show up in the gravitational waveform as subtle modulations that can be decoded with sophisticated analysis. It's like being able to tell not just that two dancers are waltzing, but also feeling the vibrations of other dancers on the same floor. The most extreme environments are the accretion disks around supermassive black holes. Here, gas spirals inward at tremendous speeds, creating a hot, dense environment where smaller black holes can be captured and merged. These wet mergers, as they're sometimes called, could be accompanied by spectacular electromagnetic displays as the merging black holes plow through the surrounding gas. They might even trigger the formation of jets, narrow beams of particles accelerated to near-light speed that could be visible across the universe. The implications for our understanding of gravity continue to unfold. While general relativity has passed every test so far, physicists know it can't be the complete story. At the quantum scale, gravity must behave differently, but we don't yet have a quantum theory of gravity. Black hole mergers probe the regime where quantum effects might start to become important, potentially revealing deviations from Einstein's predictions. Some theories of quantum gravity predict that black holes might not have true event horizons, but rather fuzzy boundaries where quantum effects become important. Others suggest that the singularities at the centers of black holes might be replaced by some form of quantum structure. If these ideas are correct, the gravitational waves from merging black holes might carry subtle signatures of the quantum nature of gravity, signatures that future, more sensitive detectors might be able to detect. The connection between black hole mergers and dark matter is another frontier of research. If dark matter consists of primordial black holes formed in the early universe, then LIGO and Virgo might be detecting dark matter interactions directly. Some researchers have suggested that the rate and mass distribution of black hole mergers is consistent with a significant fraction of dark matter being in the form of black holes. While this remains controversial, it's a tantalizing possibility that would solve one of the biggest mysteries in cosmology. The cultural and philosophical impact of discovering black hole mergers extends far beyond the realm of science. For the first time in human history, we are directly observing events that were once thought to be forever hidden from us. We are witnesses to the most violent transformations in the universe, and this knowledge is reshaping our understanding of our place in the cosmic order. Consider the profound shift in perspective this represents. For thousands of years, humans looked at the night sky and saw eternal, unchanging perfection. The stars were fixed, the heavens were immutable, and Earth was separate from the cosmic realm. Now we know that the universe is dynamic, violent, and constantly evolving. Black holes, once thought to be mere mathematical curiosities, are real. They collide, and we can detect their collisions from billions of light years away. We are not separate from the cosmos. We are part of its ongoing story. The international collaboration required to detect black hole mergers is itself a testament to what humanity can achieve when we work together. The LIGO scientific collaboration and the Virgo collaboration include over 1,000 scientists from more than 100 institutions in 20 countries. They share data freely, work across political boundaries, and pursue knowledge for its own sake. In an era of increasing nationalism and division, gravitational wave astronomy stands as a beacon of international cooperation. The technological spin-offs from gravitational wave detection are already benefiting society in unexpected ways. The ultra-stable lasers developed for LIGO are being adapted for precision manufacturing and quantum computing. The vibration isolation systems are being used to protect sensitive equipment in other fields. The data analysis techniques are finding applications in finance, medicine, and climate science. Even the vacuum technology, LIGO, has the largest ultra-high vacuum system in the world, is advancing our capabilities in other areas. But perhaps the most important impact is on human imagination and aspiration. Every detection of a black hole merger is a reminder that we are capable of extraordinary things. We have built instruments sensitive enough to measure distortions smaller than an atomic nucleus. We have developed theories that accurately predict events happening billions of light years away. We have, in a very real sense, given ourselves a new sense, the ability to hear the universe through gravitational waves. This new sense is revealing a universe far richer and more dynamic than we ever imagined. Before LIGO, we knew of only a handful of black holes in our galaxy, detected indirectly through their effects on companion stars. Now we know that black holes are merging throughout the universe, possibly hundreds of times per day. The cosmos is alive with these events, a constant chorus of chirps and ringdowns that we are only just beginning to hear. The future possibilities are even more exciting. As our gravitational wave detectors become more sensitive, we'll be able to detect not just the mergers themselves, but the years-long in-spiral phase that precedes them. We'll be able to study how black holes orbit each other, how their orbits decay, and how the surrounding environment affects their evolution. This will give us unprecedented insights into gravity, space-time, and the populations of black holes throughout the universe. The next generation of detectors will push our reach even further. The Einstein telescope, planned for construction in Europe, will be able to detect black hole mergers from the edge of the observable universe. It will see mergers from the epoch of the first stars, when the universe was just a few 100 million years old. We'll be able to trace the growth of black holes from the cosmic dawn to the present day, understanding how these objects evolved alongside galaxies and stars. Space-based detectors like LISA will open up an entirely new window on the gravitational wave universe. While ground-based detectors are sensitive to high-frequency waves from stellar mass black holes, LISA will detect low-frequency waves from supermassive black holes. These monsters, millions or billions of times the mass of the Sun, lurk at the centers of galaxies. When galaxies merge, their central black holes eventually find each other and merge as well, sending out gravitational waves that LISA will detect. But LISA will see more than just supermassive mergers. It will detect stellar mass black holes spiraling into supermassive ones, white dwarfs orbiting each other, and perhaps even exotic objects we haven't imagined yet. The gravitational wave sky at low frequencies is completely unexplored territory, and history shows that whenever we open a new window on the universe, we find surprises. One of the most exciting prospects is the possibility of detecting a mixed merger, a black hole merging with a neutron star. These events would combine the extreme gravity of black holes with the extreme matter of neutron stars, potentially producing both gravitational waves and electromagnetic signals. The first such event was detected in 2020, opening yet another chapter in multi-messenger astronomy. The implications for fundamental physics continue to unfold. Some theories predict that black hole mergers could produce gravitational wave echoes, secondary signals that bounce off quantum structures near the event horizon. These echoes, if they exist, would be smoking gun evidence for quantum modifications to general relativity. While no echoes have been convincingly detected yet, the search continues with each new merger. Another frontier is the search for memory effects, permanent distortions of space-time left behind after a gravitational wave passes. These effects are predicted by general relativity but are extremely subtle, requiring even more sensitive detectors than we currently have. If detected, they would provide yet another test of Einstein's theory and might reveal new aspects of how space-time responds to extreme events. The connection between black hole mergers and the multiverse is another area of speculation. Some theories suggest that black hole interiors might spawn new universes disconnected from our own. If this is true, then every black hole merger might be creating or destroying the entire cosmos. While this remains highly speculative, it illustrates how black hole mergers touch on the deepest questions about the nature of reality. As we continue to detect and study these events, we're building up a new kind of astronomy, gravitational wave astronomy. Just as the invention of the telescope revolutionized our understanding of the universe, gravitational wave detectors are opening up an entirely new way of observing the cosmos. We're no longer limited to electromagnetic radiation. We can now hear the universe as well as see it. This new astronomy is already revealing surprises. The masses of black holes detected by LIGO and Virgo don't match our expectations from stellar evolution. The merger rates are higher than many predicted. Some black holes are spinning rapidly, others hardly at all. Each new detection adds another piece to the puzzle, gradually building up a picture of the black hole population throughout the universe. But perhaps the most profound impact of black hole mergers is philosophical. These events force us to confront the temporary nature of even the most permanent-seeming objects in the universe. Black holes, which can outlive stars by trillions of years, are not eternal. They can merge, change, and eventually evaporate. Nothing in the universe is permanent. Everything is in flux, participating in the cosmic dance of transformation. As we stand on the threshold of a new era in our understanding of the universe, black hole mergers serve as a powerful reminder of how far we've come and how much further we have to go. These cosmic collisions are teaching us lessons that extend beyond astrophysics, touching on the nature of knowledge, the limits of human understanding, and our relationship with the cosmos. One of the most humbling aspects of studying black hole mergers is confronting the sheer scales involved. When two black holes merge a billion light-years away, we're detecting an event that happened when Earth was populated by nothing more complex than single-celled organisms. The gravitational waves we detect today have been traveling through space for eons, carrying their message across cosmic time. We are, quite literally, archaeologists of the universe, piecing together its history from whispers that have traveled unimaginable distances. This temporal disconnect raises profound questions about causality and connection. The black holes that merged so long ago no longer exist as separate entities. The galaxies they inhabited have evolved, moved, and changed beyond recognition. Yet their merger still affects us today, physically stretching and squeezing the atoms in our bodies as the gravitational waves pass through. We are connected to events in the distant past and distant regions of space in ways that challenge our everyday notions of cause and effect. The precision required to detect these events has pushed human technology to its absolute limits. The mirrors in LIGO and Virgo are among the most perfect objects ever created by humans, polished to a smoothness measured in atoms. The lasers are stabilized to a degree that seems impossible. Their frequency is controlled to better than 1 part in 10 to the 21st power. The vacuum in the detector arms is better than the vacuum of interstellar space. We have, in essence, created conditions on Earth that are more extreme than those found naturally in most of the universe. This technological achievement represents something profound about human nature. We are the only species we know of that seeks to understand phenomena that have no direct impact on our survival. Black hole mergers pose no threat to Earth, offer no immediate practical benefits, yet we pour enormous resources into detecting and understanding them. This curiosity, this drive to understand the universe simply because it's there, may be one of humanity's defining characteristics. The data from black hole mergers is also revealing the incredible diversity of these events. No two mergers are exactly alike. Some involve black holes of equal mass dancing a symmetric spiral before merging. Others are wildly asymmetric, with one black hole much larger than the other. Some black holes spin rapidly in the same direction as their orbit, while others spin backward or at odd angles. This diversity tells us that black holes form and evolve through a variety of channels, each leaving its unique fingerprint on the gravitational waves. The statistical analysis of multiple detections is beginning to reveal patterns in this diversity. We're starting to see preferred mass ranges, spin distributions, and merger rates that tell us about the lives and deaths of massive stars throughout cosmic history. It's like being able to reconstruct the entire forest from the sound of falling trees. Each event is individual, but together they paint a picture of the whole. One of the most exciting developments is the rapid progress in numerical relativity, the computational techniques used to solve Einstein's equations for merging black holes. What once took months of supercomputer time can now be done in hours. This allows scientists to create vast libraries of theoretical waveforms covering every possible combination of masses, spins, and orientations. When a new gravitational wave is detected, it can be quickly matched against these templates to extract the properties of the merging black holes. But we're also discovering the limits of our current understanding. Some gravitational wave signals don't fit neatly into our categories. They might be black holes merging with neutron stars, or they might be something else entirely, exotic, compact objects that we haven't imagined yet. These ambiguous events are particularly valuable because they point to gaps in our knowledge and suggest new directions for research. The role of machine learning and artificial intelligence in analyzing gravitational wave data is growing rapidly. Neural networks can now identify potential signals in the noise faster than traditional methods, and they're getting better at distinguishing real events from false alarms. As the rate of detections increases, these automated systems will become essential for keeping up with the flood of data. Looking to the future, the possibilities seem limitless. Third-generation detectors like the Einstein telescope and Cosmic Explorer will be sensitive enough to detect every black hole merger in the observable universe. will go from dozens of detections per year to thousands per day. This will transform black hole mergers from rare, celebrated events to routine observations, allowing for statistical studies that are impossible today. The space-based detector LISA will add another dimension to our observations. By detecting low-frequency gravitational waves, LISA will see supermassive black holes merging in distant galaxies, intermediate mass black holes that bridge the gap between stellar and supermassive scales, and the gradual inspiral of compact objects into supermassive black holes. These observations will connect the growth of black holes to the evolution of galaxies, revealing how these cosmic monsters shape the universe on the largest scales. Even more ambitious projects are being discussed. The Big Bang Observer, a possible follow-up to LISA, would be sensitive enough to detect gravitational waves from the early universe, potentially including signals from cosmic inflation or phase transitions in the primordial plasma. The Detectors Interferometer, Gravitational Wave Observatory, DISIGO, would fill the frequency gap between ground and space-based detectors, providing a complete picture of the gravitational wave spectrum. But perhaps the most exciting prospects are the unknown unknowns, the discoveries we can't anticipate because they lie outside our current conceptual framework. History shows that whenever we develop a new way of observing the universe, we find phenomena that no one predicted. Radio astronomy revealed pulsars and quasars. X-ray astronomy uncovered black hole, accretion disks, and galaxy clusters. Gravitational wave astronomy has already surprised us with heavy black holes and high merger rates. What surprises await as our detectors become more sensitive? The philosophical implications of black hole mergers continue to deepen. These events challenge our notions of permanence and change, showing us that even the most extreme objects in the universe are not static, but dynamic and evolving. They reveal the universe as a place of constant transformation, where endings are also beginnings and where the most violent events can also be acts of creation. The detection of gravitational waves from black hole mergers also represents a new kind of human achievement. We have developed the ability to sense distortions in space-time itself, to hear the universe singing in a register no ear could detect. We have, in a very real sense, evolved a new sense organ, one that extends our perception beyond the electromagnetic spectrum into the realm of gravity itself. This expansion of human perception comes at a crucial time in our history. As we face challenges like climate change, inequality, and the potential for self-destruction, the detection of black hole mergers reminds us of what we can achieve when we work together toward a common goal. The international collaborations that made these discoveries possible show that humanity can transcend borders and differences when united by curiosity and wonder. As we come to the end of our journey through the extraordinary world of black hole mergers, it's worth reflecting on what these cosmic events mean for us, not just as scientific discoveries, but as profound revelations about the nature of reality and our place within it. Black hole mergers are more than astronomical phenomena. They are windows into the deepest mysteries of existence, connecting the smallest scales of quantum mechanics to the largest structures in the universe. The story of black hole mergers is ultimately a story about connection. Every gravitational wave that passes through Earth connects us to events that happened billions of years ago in galaxies we'll never visit. Every detection links the most advanced technology humans have ever built to the most extreme physics the universe has to offer. Every merger we observe adds another thread to the tapestry of knowledge that humanity has been weaving since we first looked up at the stars and wondered. Think about what we've accomplished. We've built machines that can detect distortions in space-time smaller than an atomic nucleus. We've developed theories that accurately predict the behavior of objects so extreme they warp the fabric of reality itself. We've learned to read the gravitational waves like a cosmic language, extracting stories of stellar life and death from ripples that have traveled across billions of light years. This is not just science, it's poetry written in mathematics, art expressed through precision engineering, philosophy revealed through patient observation. The implications ripple outward like gravitational waves themselves. In education, the discovery of black hole mergers has inspired a new generation of students to pursue careers in science and engineering. In technology, the innovations developed for gravitational wave detection are finding applications in fields from quantum computing to medical imaging. In culture, these discoveries are reshaping our collective imagination, influencing everything from science fiction to contemporary art. But perhaps most importantly, black hole mergers remind us of the power of fundamental research, investigations driven not by immediate practical applications, but by pure curiosity. When Einstein developed general relativity, he couldn't have imagined that a century later we'd be using his equations to decode signals from colliding black holes. When the pioneers of laser technology created the first coherent light beams, they didn't know they were laying the groundwork for gravitational wave detectors. This is how science works. Each generation builds on the discoveries of the past, often in ways that would seem like magic to earlier researchers. The detection of gravitational waves from black hole mergers also marks a coming of age for humanity as a cosmic species. We're no longer limited to our immediate neighborhood or to the narrow window of electromagnetic radiation. We can now sense the universe through multiple messengers: light, particles, and gravity itself. We're developing what might be called cosmic consciousness, an awareness of the universe's workings that transcends our biological limitations. This expanded awareness comes with responsibilities. As we learn more about the universe, we also learn more about the preciousness and fragility of our own existence. Earth is the only place we know of where matter has organized itself into forms capable of contemplating black hole mergers. We are, as far as we know, the only witnesses to these cosmic dramas. This makes us not just observers, but participants in the universe's journey toward self-awareness. The future of black hole merger research promises even more profound discoveries. As our detectors become more sensitive and our theories more sophisticated, we'll be able to answer questions we're only now learning how to ask. What happens to information when black holes merge? Can we detect the quantum properties of gravity? Are there exotic, compact objects masquerading as black holes? Do black hole mergers leave permanent scars on space-time? Each answer will undoubtedly lead to new questions, continuing the endless cycle of discovery that drives science forward. We're also on the verge of connecting black hole mergers to other cosmic phenomena in ways we're only beginning to imagine. The combination of gravitational wave astronomy with traditional electromagnetic observations, neutrino detections, and even searches for dark matter is creating a multi-dimensional view of the universe. We're moving from seeing isolated snapshots to watching a continuous movie of cosmic evolution. The technological advances driven by gravitational wave astronomy will have impacts we can't yet foresee. Just as the technologies developed for space exploration gave us everything from GPS to CAT scans, the ultra-precise measurements required for detecting black hole mergers are pushing the boundaries of what's technically possible. These advances will ripple through society in unexpected ways, solving problems we haven't even identified yet. But beyond all the scientific and technological implications, black hole mergers carry a deeper message about the nature of existence. They show us that the universe is not a cold, dead place, but a dynamic, evolving system capable of extraordinary creativity. From the quantum foam of space-time to the merger of black holes to the emergence of life and consciousness, the universe displays a tendency toward increasing complexity and beauty. Every black hole merger is both an ending and a beginning. Two black holes cease to exist as separate entities, but a new, larger black hole is born. Energy that was locked away behind event horizons is released as gravitational waves that travel across the universe. Information about the merger propagates outward, potentially influencing events billions of years in the future. Nothing is ever truly lost, it's only transformed. This principle of transformation extends to our own existence. The atoms in your body have been on an incredible journey, forged in stars, scattered by supernovae, incorporated into planets, cycled through countless organisms. Now they're arranged in a pattern that can contemplate black holes merging billions of light years away. You are the universe examining itself, a temporary arrangement of matter and energy that has gained the ability to understand its own origins. As we continue to detect and study black hole mergers, we're not just advancing science, we're participating in the universe's journey toward self-understanding. Every discovery adds another piece to the cosmic puzzle. Every question we answer reveals new mysteries to explore. Every gravitational wave we detect connects us more deeply to the cosmos. The story of black hole mergers is far from over. In fact, we're just at the beginning. As new detectors come online and our understanding deepens, we'll undoubtedly discover phenomena that will challenge our current theories and expand our conception of what's possible. The universe has surprised us before, and it will surprise us again. So the next time you're outside on a quiet night, remember that the space around you is alive with gravitational waves from distant black hole mergers. Ripples in space-time are passing through your body right now, carrying messages from cosmic collisions that happened before Earth existed. You are connected to the most extreme events in the universe in ways that would have seemed like fantasy just a generation ago. This is the gift of living in this moment of history. We are the first generation to hear the universe's gravitational symphony. We are witnesses to cosmic dances that have been hidden since the beginning of time. We are explorers of a new frontier, not in physical space, but in the realm of knowledge and understanding. The discovery that two black holes can merge into one is more than a scientific fact. It's a profound statement about the nature of reality. It tells us that even the most extreme objects in the universe are not isolated but connected. It shows us that transformation is possible even in the most unlikely circumstances. It reminds us that we are part of a universe that is far stranger, far more beautiful, and far more interconnected than we ever dared to imagine. As we close this exploration of black hole mergers, remember that this is not an ending, but an invitation. An invitation to stay curious, to keep questioning, to never stop marveling at the universe we inhabit. The cosmos has many more secrets to reveal, and the story of black hole mergers is just one chapter in an epic that will continue as long as there are minds capable of wonder. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. We just found out how big the Milky Way is. In this video, discover the true scale of our cosmic home, from its true diameter and hundreds of billions of stars to its massive dark matter halo and supermassive black hole at the center, and much more. See you there.